Hey everyone, welcome to the last video, the second and last video for section 5.4. In this video, we're going to cover the two cases we left off last time, the case of having repeated roots for Euler equation and the case of having complex valued roots for Euler equation. Now, since we haven't actually done sections 3.3 and 3.4 yet, this is going to be a little bit strange and a little bit sort of rushed over, but I'll hit you the points you need to know for this section here, and then when we hit those actual sections, we'll do the two sets up in more detail. So let's go ahead and jump on into it. So what we want to start with first is the case of having repeated roots in the Euler equation. And so we're going to assume that r is our root, and so we know that x to the r is a solution. Now, as I mentioned before, in one of the earlier videos, one solution isn't enough, right? We need at least two solutions to be able to figure out everything else. We need exactly two, but getting a second one's an important thing to be able to hit every initial condition we want. So we're going to do something called the reduction of order method to find our second solution. And what this is going to entail is means we're going to look for a solution in the form y equals some function v of x times x to the r. So x to the r is a solution. We're going to look for a solution that is some function multiplied by x to the r. You could do this for the other cases too, but it works out easiest for this case. It actually shows something in this case here. So let's take derivatives of this, and then we'll plug it in and see what we get. So if I take the first derivative, I get that y prime in this case is v of x times r x to the r minus 1 plus v prime of x x to the r. I will take a second derivative, and I get v of x r minus 1 x to the r minus 2 plus a v prime of x r x to the r minus 1, and I'm going to get two of those, one from the first term, one from the second term, and then plus a v double prime of x x to the r. Now I want to take all of this and plug it into the Euler equation and see what pops out. So plugging these guys in, I get that L of y in this case is going to be x squared times v of x r minus 1 x to the r minus 2 plus 2v prime of x r x to the r minus 1 plus v double prime of x times x to the r plus an alpha x times y prime v of x r x to the r minus 1 plus a v prime of x times x to the r plus a beta v of times y v of x x to the r is going to be 0. Now what I want to do is I want to group all the terms with the same power of x's together. So let's start with an x to the r. So what do I have on that? Well, the first term here has an x to the r minus 2 times x squared, so that goes here. V of x times r minus 1. In the next term, my first one also goes here, plus v of x r just times r, because the x is already accounted for. And then my last term goes here, plus beta v of x. Now I can go up one power, plus an x to the r plus 1 of 2v prime of x r, which comes from the first set, and a v prime of x from the second set. And then I get a x to the r plus 2 term, which just comes from that first term, v double prime of x. I am missing an alpha here and an alpha here from my coefficients from above. All right, so now what I want to do is I want to pull the v of x out of that first term and then see what I have left over. So this is the same as x to the r, put the v of x at the end just to make it clear, r times r minus 1 plus alpha r plus beta v of x plus an x to the r plus 1 times 2r plus alpha v prime of x plus an x to the r plus 2 v double prime of x. Now, what do we see if we look at this? Well, this first term here is the exact polynomial we had for solving for r in the first place. So we know that r solves this. So this is equal to 0 because of r being the solution that we had in the first place. And the second thing we can look at is, what is this 2r plus alpha? Well, if we go back to our setup from before, right? But also, what is our characteristic equation for Euler's. I'm going to use s because I already used r as my variable. So our equation that we wrote before was s squared plus alpha minus 1s plus beta equals 0. However, we assume that we had a repeated root at r, which means this is the same thing as s minus r squared, which we can expand out as s squared minus 2rs plus r squared. So if we match up coefficients here, this tells me that minus 2r equals alpha minus 1, or 2r plus alpha equals 1, which now I can plug into that. So what all of this tells me is that x to the r plus 1 v prime of x plus x to the r plus 2 v double prime of x equals 0. Or if I take this and want to cancel out r plus 1 factors of x from everything, I get that x v double prime of x plus v prime of x equals 0. Now we can think of this as a first order equation in v prime. Right? V is not mentioned anywhere, so it's v prime and v double prime. So I can solve this like I would solve a normal first order equation. And so this we've done before. The solution here, which you can probably almost see, this left-hand side is just x v prime prime. So x v prime is a constant, v prime is c over x, and I can integrate this one more time, which gives you that v is going to be c log x plus a constant. Okay. So now this is v. What was I looking for? I was looking for a solution of the form v of x times x to the r, and I don't just want to get x to the r again. So the constant term is not what I want, because if I put the constant term, I just get x to the r again. So what I care about here is the log term. So this says that x to the r log x is also a solution. Now, is this what we want? Well, what do we have to check? We have to check the Wronskian. If the Wronskian is non-zero, then we're in good shape, and you can work out on your own again. The Wronskian of x to the r and x to the r ln of x is just x to the 2r minus 1, which is not 0. So we're good, and in this case, so for repeated roots, our general solution is y is c1 x to the r plus c2 x to the r log x. All right, there's the case for repeated roots. That was a while to get through all that, but this method we will see again when we do repeated roots for constant coefficient equations in the next section. Now we want to tackle complex roots. And the issue with complex roots is I still want to do x to the r, but now r is complex valued. So we don't even know what x to the r means. So what we're going to do is we're going to use some properties of complex numbers to simplify this and make this look better. So the extra video for this section is going to be a third video that's posted after this. It's going to be a basic introduction to complex numbers and things you need for this class, for this chapter, basically. And so I'm going to do some of the properties here, and I'll do them again in that video in more detail so you can see them worked out. So assume r is going to be lambda plus or minus I mu. Because they come in complex pairs, I can just pick one of them and go with that. So I'm going to take the plus sign here. Now the key property, which also holds for real numbers, is that x to the r equals e to the r log x. Right, you put the r up top, the e and the log cancel, and we're good. Now this is defined for real numbers and for complex numbers, actually, for r. So this is e to the lambda plus I mu log x, which is going to be e to the lambda log x, e to the I mu log x. Now this part here is nice. This is just back to x to the lambda, and since lambda is real valued, we're good there. The question is, what happens to the e to the I mu log x term? And this is something I will talk about in the next video, and it becomes sines and cosines. This follows Euler's formula, which we'll talk about in that video as well. So this is cosine of mu ln x plus I sine of mu ln x. So for my solution x to the r, I get this. So my solution is this complex valued solution. X to the lambda times cosine of mu ln x plus I sine of mu ln x. Now, in the last video for section 3.2, I emphasized a point about complex valued solutions. And that point was that if my value should be real and I get something complex, what I want to do is I get the real part as a solution and the imaginary part as a solution. And those are my two independent solutions that are going to work out fine. So we want to say our general solution is y equals c1 x to the lambda cosine of mu ln x plus c2 x to the lambda sine of mu ln x. Because I pulled out the real part and got the first with the cosine. The imaginary part got the second with the sine. Now, again, to say we're good, we have to check the Wronskian. And if you check the Wronskian of these two guys, you just get mu x to the 2 lambda minus 1, which again is not 0. So we're good, and our general solution looks like this, where the roots are lambda plus or minus I times mu. All right, so that's it for this video. Those are the two other cases, the repeated root case and the complex root case. I'm going to give you two problems to work through. Hint, it's probably one of each. One's going to be repeated, one's going to be complex. So take a look at those, fill those out, follow the formula either here or the formula I talked about earlier for repeated roots, and that'll give you the answer. So let me write that problem up for you right now. All right, so here's that problem for you guys. Two examples, figure those out, find the general solutions. It should be following the formulas that I gave you earlier in the video. All right, so if you want to watch the next video, you should. The next video is going to be about the complex numbers and what they are, what they do, why they're important, and how we get to Euler's formula, which I just kind of used magically on the last page to convert an e to the I something into a sine and a cosine. So I'll go through all that, and you can look at that for your information. Thanks a lot for watching, and I'll see you in the next one.